Okay, so this is our handout. It shows us how to move a graph or change a graph. Okay, for example, we have these 9 or 10 now flashcards, right? So you have graphs for all of these, except x to 7. But you have 10 flashcards. Imagine if I were to ask you to graph like root x plus 14 or something. Would you have to make a new flashcard or make a new table? No. You can just take the old graph and move it. So you just have to know how. Okay? So this kind of spells out everything you would do, and it's very specific. So what I mean by that is it tells you how to move up by a certain amount, and how to move down by a certain amount, how to move left, and how to move right. It talks about how to reflect for the x-axis, how to reflect over the y-axis. It talks about how to do compression and stretching, both in the horizontal and vertical case. It has everything. It tells you exactly what to do. It tells you how to write it. It's got everything. Okay? Pretty nice to have. It's also very, not only is it specific, but it's also, in a sense, very generic, because I never said what f of x was, right? It just says f of x. So that means it applies to any and all graphs. Okay, so it's a very versatile yet very specific page. Okay, title of the lesson is 2.5 Graphing Techniques, Transformations. So you can write that down on your paper. We will not finish this section today. You might not even learn that much new stuff today. You might have already seen some of this, even as early as pre-algebra. So, it's just so important, we plan to restate it and then build on it. Okay, we've got the title. It's also on top of your handout, Graphing Techniques, Transformations. Okay, so just for this particular lesson, I recommend you not have your graphing calculator out, because your graphing calculator will give you the answer to every question, and you kind of lose out on the meaning sometimes. So you can use your graphing calculator to check the answers if you want. Okay, there's our title, there's our handout. Let's go to the first example. So find a function that is finally graphed after the following 3 transformations are applied. And I think I'm actually just going to change this to 2 transformations. We'll just do these first 2 transformations. We're going to transform y equals absolute value of x. Okay, so I did not have to draw this for you because you already know this graph. Passes through these 3 points. I call these the 3 amigos. Okay? -1, 1, 0, 0, 1, 1. So if I were to ask you to shift this left 2, I mean, any 4th grader would understand that. You're just going to move it over to the left 2 spaces, right? But what happens to the function? So y equals absolute value of x would become y equals absolute value of x plus 2. Why? Because according to the handout, a left shift is obtained by adding a number to x. That causes the graph to move left 2. Okay? And if you want to draw it, you can. It'd be over here now. The 3 points all shift left 2 spaces. But honestly, the drawing's not as important to me right this minute as the way you write the function. Okay, is that the same thing as writing it this way? Let me write it this way now. Do you think that's the same as writing this? If I accidentally put the plus 2 out here, you think that matters? If you put that plus, if you write it like absolute value of x plus 2, instead of x plus 2 on the inside, yeah, you're messing with it. This is not what you're supposed to do. Okay, this is not the same thing. That actually would be an upshift by 2, as we'll see as part B here. Okay, so you have to be really careful where you put your addition. Is it surprising to you that adding 2 to the x would cause the graph to go to the left? Does that surprise you a little?
No, because isn't it y minus h? No, y minus x, h minus.
Okay, what's actually going on here is, well, addition would mean move in the positive direction, and subtraction would mean move in the negative directions. But x right here is what we call implicit. It's buried in the function. Okay, right now it's stuck inside of something. So if you adjust it, it's going to behave opposite of what you'd expect. So x is sort of the buried variable. And if you were to add to it, the graph's going to go left. If you were to subtract from it, the graph will go to the right. If you were to multiply it by 3,000, you would think that everything would get really wide, right? X is being multiplied by 3,000, but actually everything collapses narrow. Everything seems reversed for this buried variable. Okay? And if you were to isolate x, then things would behave intuitively, like the way you would expect. All right. We can't go into that too much, but let's go on to the next example. So on the next one, we're supposed to shift up 3. See if you can find that on your handout. Up 3. So here's your handout. Just find shift up. Where is that? It's our very first one, right? Okay. So it looks like we're just supposed to add the number on the outside of the function rule. Okay, so let's go back to our problem. Y equals absolute value of x would then become y equals absolute value of x plus 3. So here we are adding to the outside. That's a vertical shift. And it is up. Interesting. So you might argue, well, hold on, Mr. Shore. I thought addition made you go in the backwards direction. So wouldn't that mean down? No, y is isolated. So if you're going to do a vertical motion, it's going to behave exactly like you think adding 3 moves up 3. It's only for the x that's buried where it can seem backwards to us. Okay, if you don't fully understand what I'm saying about the implicit variable and the explicit variable and all that, it doesn't matter. If you have the handout, you can just go over it and add 2 means left 2, or add 3 means up 3. Just follow the handout very literally. If you really want to understand it, you can go back and watch this video again and listen to what I said about the buried variable and the isolated variable. Okay, so that's a pretty simple example. You can just follow the handout and get them both right. Let's go to the next problem. So what about this one? This is no longer an absolute value function, but remember what I said. The rules work for all functions. Okay? So the first thing you want to do on this is just identify your parent function. So you want to figure out which flashcard does this most resemble.
Go to x squared.
Yeah, this would be the x squared flashcard, right? When you look at it, it's x squared, blah, blah, blah. The fact that there's an x squared means it's degree 2, and the only card we had was the x squared card. Okay, so if you know what that graph looks like, that will spare you the hassle of making a new table, right? In Algebra 1, you would have gone like this, maybe, and you would have made up some x's. Maybe you ask your teacher, which x's do I pick? Okay, we don't need this anymore. Okay, we know what x squared looks like. We just need to understand what minus 4 means. Okay, so are we taking away 4 from the function, or are we taking away 4 from x? There's a difference. Look at the picture here. What do we got? I mean, look at the equation. Are we taking away 4 from the function, or 4 from x? This is 4 taken away from the function. So this would mean down 4. I'm not saying it's x minus 4 with a square on it. It's x squared and then take away 4. Okay, so this is a down 4 shift, and that makes the problem very easy because you're just going to move the graph down 4. Okay? This is a very powerful technique, okay? Because it really changes kind of the way you look at new graphs. In Algebra 2, when there was a new graph and you didn't know what it looked like, you would just make a table like this. But maybe we can just start memorizing a few, like a handful of graphs, maybe 20 graphs or something, and just move them around. That's got to be better. Yeah?
You know that down 4 because it's not x minus 4 squared, right? Like if it's been in parentheses.
Yes.
If it was over 4 to the left and 4 to the right, it would have been in parentheses, and the square would have been outside, right?
That's right. So this would be, if you see this, oops, x minus 4 squared, this would mean right 4. It's not the same thing as what I have here. Okay? Yes. Other question? Okay, so you always ask yourself, is it x that's being modified? Because if it is, it's a sideways motion, right? If x is being changed to x minus 4, then that's going to affect the horizontal nature of that graph. It's going to slide sideways, you know? But if the function, aka y, if the y value is having 4 subtracted off it, if the function is having 4 taken away, then the y's are all going to change and the graph's going to move up or down, see? Okay. So I'm going to erase this just because it's not relevant to our specific question. But let's look at this next one. Oops, I went too far. Where's my example? It went away. Well, that's okay. I will rewrite this one. I want to do another parabola before we do a different style of graph. Okay, now let's change this problem to, let's make it x plus 2 squared plus 1. Let's try that. I thought I had that example in here already, but no, I just added it in. This is our next example. So you guys agree that this is still an x squared function, right?
Yes.
Okay. Let's treat it as a same parent function. So it's still y equals x squared, it's just transformed. Okay? So we just have to understand what x plus 2 means. What does x plus 2 do to the graph? It's going to modify your x's. It's going to be a left or right shift, specifically left shift, right? So this means left 2. And what does this out here mean? Up 1. That's right. So left 2 and up 1 for the x squared graph. So that sort of puts your graph over here instead of at the origin. And you can still draw those 3 amigos points, right? These guys. Okay, let's see. What if a person gave you this problem? So what if you are given y equals x squared plus 4x plus 5? What do you do with that? Can you still do this method? What do you guys think the shifts are on this graph here?
Could you factor it and then?
Okay, so we've got a couple things. First of all, your first thought might be, oh, it's going to go like up 5, right? But look, let me cover up the plus 5. Does that say x squared?
No.
No. This is not quite the right format, is it? Like, this doesn't quite look like that. I assure you, this is the same exact problem as that
Wouldn't
one.
you subtract 5 to the other side and then square, take out an x, factor out an x and x squared plus 4?
You're on the right track. If we can make this look like that, then we can apply the transformations. Okay? So what you would do on this is complete the square. You guys might remember that. What you do is you just kind of leave the 5, just put it over here, and then what you do is you take half of this and you square it. So what's half of 4? What's half of 4? 2. Square that, you get 4, right? So you put in a 4 right there and a minus 4 right there to keep things balanced. And then what happens is this first part now factors nicely into x plus 2 squared. That's this first trinomial. And then there's your plus 1. So this was the exact same problem in disguise. It is that problem. I just had it foiled out, see? And when it is foiled out, you can't use the transformations really, but if you can write it in factored form, you can see, hey, that's left 2 up 1. So you can apply it to a lot of graphs, even when they're foiled out. So this is the same problem, is what I'm saying. Okay, we're getting a little bit ahead of ourselves. My point today was not to teach you how to transform equations into this format. My point today was to show you that when they're in this format, they're easy to graph. Okay, let's look at the next example. Remember, I never said what f of x was, right? So it doesn't just apply to parabolas like we've been showing. It would apply to this graph also. So some of you have seen this graph in Ms. Chen's class, right? Does anyone know what graph this is? It passes from the origin, it goes through pi, 2 pi, and 3 pi. And then the y value here is 1, and the minimum y value in this graph is negative 1. Has anyone seen this graph before? What is it like?
Is it the sine graph?
Yeah, this is the graph of sine x. We're not learning trig right now. We're going to learn it next. We're actually skipping straight from chapter 2 to chapter 5. So that's what we'll be doing. We'll learn this graph sooner or later. We'll even have a flashcard for it. But it doesn't matter if you've seen it or not. The rules still apply. What does it mean to have x plus a number? What does the handout say? What is x plus a number? Shift to the left by that number. That's what it means. Okay, so we're not going to let this stuff intimidate us. This means shift left by pi units. That is not going to be hard to do. The x-axis is already measured in pi's, so this goes 1 pi, 2 pi, 3 pi. Let's just move everything over one space, and we'll be done. So let's move like this. This point is going to be over here. Okay, so the first point. Oh, let me show you what I'm transforming. I'm transforming these 4 points. I figure if I move these 4 black points, that's good enough. I'll just draw the wave. Okay, so I just moved the first point left 1 space on the x-axis. Then I'm going to move this point left a space. Okay, so it's going to go here. And then I'm going to move this 2 pi over to pi. And I'm going to move the 3 pi back to 2 pi, and then connect the dots again. So it's important to understand, I'm not modifying the shape of the graph. I'm not modifying anything about it except its position, like where it was on the graph paper. That's the only thing I'm trying to change here. It's just strictly a rigid shift to the left. And there it is, there's your answer.